This video covers aldol reactions. We're going to discuss the two reactions that fall into this category, making a product like the one we have highlighted on this slide, and the second reaction is going to be a condensation reaction resulting in an alkene product. So, if you remember from previous lectures, in the presence of base, the alpha position can be deprotonated to form the enolate anion. And just as a reminder, I'm going to draw what the enolate of this aldehyde would look like over to the side. And of course, we know that that can tautomerize, but frequently we'll see it drawn this way. Remember that our carbanion is a strong nucleophile, and we had previously talked about how we actually have an equilibrium between the original aldehyde and the enolate, which means that these two molecules can react with one another, which is what's being illustrated for the product. When an enolate reacts with another molecule that has the carbonyl, it attacks at our partial positive carbonyl and forms a new bond between that alpha position in the original enolate and what used to be the carbonyl carbon. So in our product, what is now labeled a beta position for the new molecule is the same as that carbon that I just starred on the original aldehyde. The product of this reaction is a beta hydroxyaldehyde because at the beta position of our new final product, we have a hydroxide functional group. The product features an aldehyde right here and also an alcohol, which is where the term aldol reaction comes from. You're making a product that contains both the aldehyde and the alcohol. Mechanistically, this is what's happening. So I had drawn out the enolate on the last slide, but this is how we're getting there in case you needed a refresher. Our base is going to catalyze the reaction, do the deprotonation step, and for this particular mechanism, it's really common to see our enolate drawn with the lone pair on that alpha position. We see our nucleophilic attack happening with another molecule of the aldehyde, and that forms our new bond at the alpha position. And now we have a beta position because we've grown that carbon chain by two carbons, the two carbons that were in the new aldehyde that underwent the nucleophilic attack. Of course, as a result of not overfilling the octet at what used to be the carbonyl, we now have to do a proton transfer to get rid of the negative charge on the oxygen that used to be part of that carbonyl functional group, and that's how we get our alcohol on the beta position. So this is the complete mechanism for the aldol reaction. Generally speaking, for our aldehydes, the aldol product is favored. So here we see our equilibrium is favoring our products. And the question on the slide is asking you to think about kinetics and thermodynamics and how temperature could affect the equilibrium. Generally speaking, remember that as we increase temperature, more of our molecules have activation energy required to complete the reaction. And so equilibrium should be driving our reaction towards our products. For our ketones, we do not see the same equilibrium ratio. Generally speaking, our ketones are favored as opposed to our product, which in this case is a beta hydroxyketone instead of being a beta hydroxyaldehyde, because of course this is our alpha position and there's that beta position again in the final product. I think on this structure, it's perhaps a little bit easier to see our new bond that was formed we have a couple of practice problems coming up, and I'll try to help illustrate where we have the carbons from both of our starting materials coming together. So in the case of our ketones, it's more common to see what's called a retro-Aldol reaction, basically breaking your product up into the original ketone. And of course, this would be breaking up into original ketones that are identical to one another. That's cyclohexanone. So here we have an example problem asking for us to consider our products, what the product could be, and also then what the mechanism could be. First, let's think about our products and identify all of our alpha positions. And then I've got the mechanism that we'll show on the next slide. So this is an aldehyde. That means we only have one alpha position right there. I'm going to draw out that hydrogen. And our hydroxide would deprotonate that hydrogen, or that position, the alpha position. So it may be useful for us to draw what that enolate product would look like, that deprotonated product. So we don't have any other carbon-containing molecules. That means that this enolate is going to react with the aldehyde as they both exist in equilibrium. So our new final product should still have all of the original carbons. Here's that. So we can think of this molecule as belonging to the enolate. And then we have the lone pair that's going to do an attack. Here's our new bond, and I've exaggerated it a little bit, that is going to form between our negative charge on the alpha position and the carbon that used to be the carbonyl carbon. So that means that coming off of the carbon right here, we need to have an alcohol followed by the carbon chain. And then we have 1, 2, 3, 4 carbons total. So this is starting a new molecule. There's 1, 2, 3, 4 carbons total. And on that second carbon, we would have a methyl position. So here's what our final product would look like. Mechanistically, this is what the mechanism would look like. So we know that we can deprotonate and form the enol. This time, the enol is being drawn in the double bond form instead of showing it as the lone pair the way we did in the last mechanism. So that lone pair we know is nucleophilic. We've refreshed over that, and so it can still attack at the carbonyl carbon, moving the electrons on between the pi bond and oxygen and carbon up onto the oxygen, so we don't violate the octet rule. That leaves us with an alkoxide that needs to be protonated and gives us our final product that is that beta hydroxy aldehyde. So I have a note here to remind us to think about this. So here, this carbon is sp2 hybridized. So the stereochemistry that we had specified earlier ends up going away due to the trigonal planar nature of the sp2 hybridized carbons. likewise, when we do our nucleophilic attack here, we would end up with a racemic mixture of our, since it's attacking at the sp2 hybridized carbon, we have them drawn as straight lines here, but we know that the attack, we could illustrate it with the wavy lines or draw one enantiomer and say plus En if we wanted to. And if that was the case, remember this right here was the bond that had originally been the wedge, and so then you could also have a plus En since this carbon is a chiral center. So we can make these beta hydroxyaldehydes, which is the starting material on this slide, and we know that our alcohols can be involved in elimination reactions. That is precisely the next reaction that these aldols can undergo. This can be done under basic conditions or under acidic conditions, and usually we see a little bit of heat applied in order to get the reactions to proceed. So our product then is what's called an alpha-beta unsaturated carbonyl. Carbonyl is a broad term since we could do this with either aldehydes or ketones, although we know the aldehydes are more favored. But remember, the double bond is between the alpha and the beta position. While, yes, we have hydrogens on the gamma position, the alpha position is going to be the preferred place to pull off a hydrogen in this elimination because we create that conjugation of double, single, double, single. So here, as we have started counting, including our oxygens, if I could count, that would be useful. We end up with 1, 2, 3, 4 with pi bonds between the 1 and 2 and between the 3 and 4. So here we have reaction conditions for acidic and basic condensation. And just as a reminder, condensation reactions yield some kind of small molecule. In this case, it is going to be water, but we have seen some other condensations throughout the semester that gave us a small product of nitrogen, for instance, nitrogen gas or CO2 gas, something like this. So for these products, for this reaction, it's asking us to predict what our product would be, and then I have space on slides following up to draw out what that mechanism would be. Hopefully you realize that both of these beta hydroxyaldehydes are identical, and so our final product should be the same. So I'm going to draw the product kind of in the middle of those. Your carbon chain doesn't change. Your carbonyl doesn't change, but your alpha and your beta positions will now have a double bond in between them. Mechanistically, how we get there, that is different, but the final products are the same. So let's practice the base catalyzed mechanism for this. And as a side note, sometimes you will see the base catalyzed version of this mechanism referred to as an E1CB mechanism. What that means is that your enolate is going to, your enolate is a conjugate base, so that's what the CB stands for. And generally speaking, the elimination could be occurring through the E1 mechanism. It partially depends on what the structure of the molecule looks like. So our mechanism should start out with our hydroxide, and I'm going to draw back in our alpha hydrogens. So we're going to do a deprotonation here, and we'll draw effectively that enolate getting recreated. So mechanistically, that yields this. with a lone pair back on the alpha position. Now, that lone pair, instead of acting as a nucleophile, is more likely to immediately react with its neighboring carbon and form a pi bond instead of acting as a nucleophile, because we have a molecule, or we have part of the molecule that can act as a leaving group. It's not necessarily the best leaving group, but it is certainly a possibility. And remember, there's a major motivating factor behind creating this conjugated pi system that we're able to do. So I've got the pi bond being formed. Of course, that now means that we need to move our electrons onto the alcohol. So we are mechanistically losing our OH minus, and that will now give us our final product that looks like this, that alpha beta unsaturated carbonyl. I've made a slide where you can practice the acid catalyzed version of this reaction. This reaction provides you with some really nice review from chapter 7. If you recall, we talked about some special elimination conditions for alcohols specifically that requires a catalytic amount of acid. So feel free to pause the video or come back to it and practice this on your own time. So when we're making our alkenes, we of course can create two different stereoisomers. We can think of these as E versus Z. Technically, with the hydrogens, we could think of them as cis and trans, since we do have the same group. Think for a minute, which one of these do you think would be the major product? Hopefully, you guessed the E, or the trans product, would be the major product, and then the cis product would be the minor product. The way that your molecules are typically in the lowest energy state, we have our largest groups on opposite sides of the double bond. Think about what our mechanism looked like. I'm going to go back 2 slides for us to look very briefly. We want our elimination to, we have our alcohol that is leaving, and it's furthest away from that lone pair, so that the lone pair has plenty of space. In this configuration, that means that the methyl group will automatically be pointing away from the rest of the carbonyl structure. So mechanistically, having the trans or the E product, that would be favored. So we've talked about creating our beta hydroxide, our beta hydroxy aldehyde, and the fact that we can do a condensation reaction afterwards. In reality, it can often be very difficult to isolate these beta hydroxy compounds. And in fact, a lot of times they're not isolated at all, the way that I have it designated on this slide. So a lot of times, these reactions, you will be expecting to get the elimination product where you are forming this double bond. Through, again, if this is base catalyzed, the way it's indicated, that's that E1CB, where the enolate is acting as a conjugate base. E1 now kind of reminding us that this is a 2-step mechanism, forming that lone pair and then the loss of leaving group occurring. So, this can be pretty useful in terms of forming conjugated molecules. We've already seen that. And the example here, we would assume that this product would be very highly favorable because now we have what we're calling an extended conjugated system, where one ring is fully conjugated And then, we have another double bond, one away from the ring, and then the conjugation extends on to the double bond created through our condensation, and that goes all the way over to the right side of the molecule. We'll talk more about the spectroscopic consequences of this extended conjugation when we cover chapter 16 at the end of the semester, but think in terms of stability, what conjugation does for the benzene ring, and recognize that that's really going to be a stabilizing factor for these conjugation products. So on this slide, we see two different temperatures for our aldol reaction to occur at. And this is being done with a ketone. It is possible to do these reactions with ketones. It's just sometimes the yields are very low. What we see is that when we do this reaction under cold temperatures, you can get some of your aldol product. It's just very low yielding, 20%. Instead, when you do it at high temperatures, favoring that condensation, you really increase the percent yield of the alkene product and the conjugated alkene product up to 90%. So while temperature can allow us to control the product and get out that alpha or the beta hydroxy ketone product, in this case, your yield is going to be very low. So most people don't use that singular reaction by itself. Instead, we use it as an intermediate to get to your condensation product. So we kind of have this reaction. If we go back, this is the aldol reaction, and then this is condensation as a part of it. And a lot of times people will just use reaction conditions to not even try to isolate the aldol. So you may have noticed a trend. All of our reactions so far have been with one aldehyde or one ketone, so that we are yielding one possible product. But that's also not very versatile. So often we will see reactions where we're having two different aldehydes or two different ketones being used to create these larger molecules. When we do that, it's called a crossed aldol or a mixed aldol reaction. So in this case, we have two different aldehydes. We've given some base, so these will be base catalyzed reactions. We can actually create 4 different products from this. So I'm going to draw out all 4 of our products. The way that I'm thinking about this is take each one and turn it into an enolate, each one of your starting materials, and turn it into an enolate. And so the first one, I'm going to turn our smaller aldehyde into the enolate to react. So what I'm going to do is above each of these structures is draw the enolate version, so it's easier to visualize how that molecule could then react with itself, the way that we've been learning this reaction. So if we were to get this molecule to react with itself, the final product should look like this. So we can remember the enol, or the enolate rather, will keep its carbonyl structure, and then this bond that I just drew is the new bond that is forming. Here's the alcohol that gets formed, the beta alcohol, and now we have to draw in our other 2 carbons that were part of the aldehyde that underwent the nucleophilic attack. So we've got our alpha position where the lone pair used to be, and the beta position is now the original carbonyl in the aldehyde that underwent the nucleophilic attack. So that's one of the products. Another product would be for the enolate of the smaller aldehyde to react with the larger aldehyde. Excuse me, y'all. It will react with the larger aldehyde. That product will look a little different and be a little bit bigger. So we keep our smaller aldehyde enolate structure, and then we can picture it doing a nucleophilic attack. So there's my alpha position. Here's my beta. Here's where my alcohol would be. And then that larger aldehyde has 3 carbons. So we have my first one where it's attached to the hydroxide. And then here's 2, here's 3, like that. And I just use free rotation in order to create the more natural structure. So we have our alpha and our beta position, and we see that we just added 1 more carbon than in the last product. Now, to get our other 2 products, we will have our larger aldehyde acting as the enolate. So I'm going to draw in what that starting material would look like. Remember, it's going to be the alpha position that forms the lone pair. So that's going to mean we're having branching on some of these final products for these. So we have, if we were to have our larger aldehyde react with itself in the enolate form, that structure will look like this. And I'm drawing it at the bottom for a reason. So here's the original aldehyde, okay? This is the alpha position, so here's where the new carbonyl is going to form. Here's where our OH is on that beta position, and then we have 2, 3 more carbons, okay? So for the one reaction that I have space left in, that's going to be where the larger aldehyde enolate version reacts with the smaller aldehyde, the one that's in red. So if that's the case, once again, we still keep the structure of the original enolate, so the larger enolate, and then we see the beta position be what used to be the carbonyl in the smaller aldehyde. There's our new hydroxide, and that is only a 2-carbon structure. So now our alpha position has a branch point, and our beta position still has the hydroxide. So the 2 products in the middle are our crossed or mixed aldol products, and our enol is what, for these reactions, is what I am circling right now, because it retains the carbonyl. That's how you can always tell which part of the molecule was the enolate. It retains the carbonyl since it's not undergoing the nucleophilic attack. So obviously we have 4 different products. The yield on this would not be ideal. So we do have ways to control these crossed aldol reactions. One of those ways is to design your reaction in such a way so that there is only 1 alpha position that can be deprotonated. And so that only allows for 1 enolate to form and would help increase the yield on our product. So we would be seeing this acting as the nucleophile to do the attack on the carbonyl. And once again, we've got this kind of color-coded, the blue aldehyde that serves as the enolate with the alpha position is keeping and retaining its carbonyl structure. And of course, we've got 1, 2, 3 carbons, 1, 2, 3. So that is one way to control your cross aldol products. Here's another example with a much larger aldehyde that does not have any alpha protons. We still only have our propanal, to use the proper term, having the alpha position that has available protons. The alpha position on the benzaldehyde doesn't have any protons attached to it. So we do not have to worry about it being deprotonated and acting as a nucleophile. So here we see our aldol product. Again, alpha position, beta for the hydroxide, and especially with this ring being present, we can create that conjugated every other double bond. Every other bond is a double bond situation. So that is going to probably not be an isolatable beta hydroxyaldehyde, and we would go immediately to the alpha beta unsaturated carbonyl. The second way of managing this is to use a new base, the lithium base that we had talked about earlier, LDA, to create the enolate in the presence of only one molecule that contains an alpha position. Then, once that is fully deprotonated, you can add the second substrate, the second alpha position the second alpha position containing molecule. Easier to phrase it as adding in the second ketone or aldehyde, and basically that's setting up whatever's getting added second to undergo a nucleophilic attack. So you're getting a nucleophile here, and then you're seeing an electrophile getting added, right? And we've got that partial positive at the carbonyl. So we see the second molecule that got added turning into the alcohol part of your beta hydroxyaldehyde here. Now, we have this example problem. I've given you the final product, and the challenge is to now figure out what our starting materials should be. So we're looking, and I've tried to point this out to you, but here is the carbonyl, okay? This is an alpha position where we have our double bond. So we've undergone a condensation reaction. You can kind of make notes to yourself if that helps. And so we have our beta position. We know for the condensation reaction, the beta position used to have an alcohol on it, and that was part of the nucleophile. So we have our carbonyl, and in fact, I should have gone ahead and included the alpha position as part of the original molecule. So if that's the case, then we know that one of our starting materials had to contain this ring and the carbonyl, and it needs to have the alpha position that was deprotonated. Then the beta position is the beginning of the second substrate, so to speak. So here we would call this 1, 2, 3 carbons that were in the other starting material. And so the rest of this molecule, or the starting material that gave us the rest of the molecule, should once again be this propanol. Now, the way we would write this reaction out over the arrow, we would need to do something like introducing LDA first, so that we're only deprotonating one alpha position, and it will selectively deprotonate the easier access alpha position in this case. Then we introduce the second aldehyde. Now, when we're using LDA, sometimes you will see a temperature written next to it. Usually it's something very cold, like negative 78 degrees C. That is the temperature that you can achieve with by mixing acetone with dry ice or solidified CO2. So now we have our product. This would just be our hydroxy or our alkoxy product. So step 3 would be introducing some kind of workup. Water would be suitable here. And then, so this gives us, at step 3, we're now at our beta hydroxy product. Step 4, you need to use some kind of acid. And if you're using acid, a lot of times you'll see your tosylate-based acids. or base, and often you'll see heat added in order to do the elimination. We know that the elimination can happen under acidic or basic conditions. So you've got a little bit of leeway with what that fourth step should be here. We're close to the end of our aldol reaction discussion, but it should be noted that we can have molecules that are long enough to react with themselves through these aldol reactions. So if we're looking at this structure, we have an alpha position that could be deprotonated, and that alpha position is far enough away from the other carbonyl on the structure that it could react, it could fold up and react with itself in order to form a final cyclic product. And of course, using base and heat, that gives us not only conditions for making the enolate, but also then doing the elimination to produce our cyclic alkene product as well. So down at the bottom of the slide, I have illustrated for you what that deprotonation would look like. It would give us an enolate nucleophilic site, and now I've kind of rearranged the molecule so that you can see that the nucleophilic site is actually quite close to the carbonyl, the electrophilic site within the same structure. And the arrow that I'm just putting a star next to right now, that is the new bond that I put an arrow to in the original final product. And that's also why we get a branch point on the 5-membered ring instead of forming a 6-membered ring. Because we have some carbons that are coming off of that second carbonyl. And of course, this would form the beta hydroxy group at first. With base and heat, it'll undergo the elimination to give us that final alkene. That's everything for your aldol reactions.